So now let's start with chapter 6. The first session is called the volume using the cross sections. Okay, so this is a very important section, and then we want to explain the brief idea about how do we solve the volume of and revolving uh, region. Okay, but starting from the beginning, we want to introduce the concept is called the cross section. Okay, so basically, as you can see, that a cross section of a solid S is the planar region formed by intersecting S with a plane. Basically, think about you have a cardboard, and then you have a solid which the both top and bottom they are, we assume that they are parallel. So and you can see that, if you have a cardboard, and then if you make a cut, and then that intersection pieces is what we call the cross section. Okay, and also you can see that since we introduces our xy axis on this curve, realizing that if I'm moving this board, back and forth, the corresponding cross-section area is going to differ, right? So to do that, you can see that we also set x as the intersection of this board with the x-axis to denote the location of this cross-section. And also, based on the idea of the cross section, how do we figure out the volume of this solid? Well, the idea is if we have two cross sections, okay, and if we denote it, one is at x equals xk minus 1, and the other is xk, and we want to make sure that the distance between xk minus 1 and x is extremely slow, okay, is extremely small. Okay, in other words, you can think about this is the height for this piece, the distance for it's a very tiny. Okay, so if we take this part out, as you can see that this in large slab, you can see that the area of the top and the bottom, they are almost identical. In other words, what we can do is we can treat this as a regular cylinder. In other words, if I know the area of the top or the bottom because they are the same, and then time the height, which is exactly the distance between xk and xk minus 1, we can immediately find the corresponding volume. Okay, volume. And then we can borrow this idea, and then as you can see that if we make a lot of cut, we're gonna form a few slabs. Okay, and then we can use this idea to calculate one approximation of the corresponding slab part, treat as a cylinder, and then add all these volumes up, and then take a limit. So this process, basically we are working on a Riemann sum, okay, and then take that limit. In other words, let the number of the partition become infinite. If that limit exists, and then we know that that's going to be the volume of this solid. And then how do we describe that in terms of an integral? Fairly straightforward. So here's the definition. The volume of a solid of an integratable cross-sectional area AX from A to B is the integral of A from of this capital A denote the area of the cross-section from A to B. Basically, it's integral from A to B, A of x dx. Okay. So later on, when we're trying to figure out the volume of a solid, if we're trying to use this cross-section method, what we'll do is sketch the solid, and then also sketch a typical cross section. Okay, and also figure out the general formula for that cross section in terms of x. Okay, and then find the starting point A and end point B, and then set the definite integral and then integrate it, and we're done. Okay, if we apply the cross section method. Okay, so let's quickly look at one example here. As you can see that we have a pyramid 3 meters high, and it has a square base. Okay, square base. That is 3 meters on the side. So that means the height is 3, and also the length for it, the base side is 3. So the cross section of this pyramid, it is perpendicular to the altitude x meters down from the vertex, and then that cross section is also square with the x meters on side. Okay, so this is already the graph. And then the problem asks us is, okay, so figure out the volume of the pyramid. Okay, as you can tell that the cross section of that pyramid is a square, and then we know that the pyramid perpendicular to the altitude x meters down. In other words, the distance from here to here is x meters down, and then the length of each side for that square is x. So in other words, we can easily calculate out that the area of a typical cross section, which is x squared. Okay, so A of x equals x squared. And then we know that the integral is from 0 to 3. So the corresponding volume of this pyramid, which is exactly from 0 to 3, x squared dx, which is pretty straightforward to evaluate it. Okay, so I'll skip that part. So that's a starter. Now the next part is we're going to introduce a more powerful method to figure out the volume of a solid by revolving. Okay, and then so the first type is called the disk method. Okay, and then as you can see that the basic idea is, you know, if I have a region like this, okay, and we know that if I revolve this region with respect to the x-axis, and you can see that we're going to formulate a solid, right? A solid. And the problem is, how do I figure out the volume of this revolving solid? Well, as you can see, that if we borrow the idea of the cross-section, realizing that the cross-section is going to be a disk, or you can treat about as a circle. Okay, as a circle. So, you know, if the cross-section is a circle, and then we have a name for this, we call this is called the disk method. Okay, so to figure out the area of that cross-section or the area of the disk, keep in mind that as long as we know the radius, so the area is going to become into pi times the radius squared, right? In this problem, we denoted capital R of x as the radius, and then you can see that the cross-section area, which is denoted as pi square root of x squared, which is pi x. Okay. Now, of course, you know this integral is from 0 to 4. Okay, so that the corresponding integral is from 0 to 4 pi x dx. Okay, pi x dx. And yeah, so a keynote is, you know, when we apply the disk method, the integral is with respect to the revolving axis. Okay, in other words, or you know, if I revolve with respect to x-axis, or a horizontal line which is parallel to the x-axis, and then I'm gonna always apply when I apply the disk method, my integral will always be with respect to x. Okay, just to keep that in mind. And then you see, of course, we can apply the disk method if we have a area of region, and then we revolve with respect to the y-axis, and correspondingly you need to figure out the area, of the corresponding disk. And then in that case, when you drive the radius of that disk, make sure that the representation of the radius is in terms of y. Okay, because keep in mind, the integral will set it up is going to be with respect to y. So everything inside of that integral is going to be in terms of y. So that's why when we see that, okay, capital R of y must be in terms of y in this problem, which is 2 over y. Okay. And then of course, limit is from 1 to 4, so it's easy setup for this. Okay, so that's also not that challenging, And then on top of that, we actually gonna have another type of situation, that is, think about this. If I have a area between two curves, okay, and then in the previous this method, we actually set the lower curve as x-axis, okay, part of the x-axis. But right now, think about it, if we have a lower curve like this, and if I revolve this region with respect to x, and you can see that we're gonna have a solid in this one. In other words, this part actually is empty, okay? So how do we figure out the volume of this type of solid? Well, as you can see that if we draw a cross section, that's gonna be, looks like a band, right? So we have a name called this shape is called a washer, okay? And how do we figure out this volume? Well, pretty straightforward. You think about it, well, if you can calculate the volume of the solid for the outsider, they're gonna give you the volume for the whole piece, including this missing part. Meanwhile, if you can calculate the volume of the revolving solid based on the lower curve here, you can see that you're going to calculate the volume of this inner piece. If you make a difference, that's going to be exactly what we need, okay? So this is what we call the washer method, okay? I think there's a typo here. So the washer method, the integral is also with respect to the revolving axis, okay? So for this problem, I'm going to do the integration from a to b, pi times capital Rx squared minus small rx squared dx, okay? So that's some curve here. Yeah, so I think this should be good for this 6.1, and so hope you enjoy this, and thank you very much. Have a great day.